the transition of the wind-driven ocean circulation, please.
Okay, have a look in here. Yeah. Okay, well, it is a pleasure giving a talk for the audience. I realize how important it is. I tried to find some subject, which would be interesting for many of you. I mean, it has to do with climate motivated. It has to be, models which are familiar to you and should be intermediate complexity. And should be some interesting phenomena. So I often come down then to, the wind-driven ocean circulation, which you all know from textbooks. I mean, here you see the currents in the Atlantic and the Gulf Stream. Pacific, you see the Curaçao, it's sort of the brother of the Gulf Stream in the Pacific. And we're going to look at, say, phenomena in these currents. And this is work done by a group which is active in the Critical Earth and TPES project, which are European projects. And there's several PhDs and postdocs and also some American mathematicians in the north of the country, the Netherlands, where I'm from. So we're going to focus very shortly, because I don't want to do too much, climate dynamics, or really, because if many of you are not familiar with that. But to show you this phenomenon of the path variations of the Curaçao, these are bi-weekly, say, contours of a sea level, say, ISO curve, so sea level height. And if you plot those, these are determined by satellites, altimetry. And when you see sort of these patterns, you see that, well, sometimes, it's in a sort of meandering state, a Curaçao, like a very sort of irregular state. And sometimes it's a very straight path here, for instance, in 2003, 2004. And here you see the meandering state here in 2000. And so you see already from this sort of pictures that it varies on the decadal scale. And there's some longer time series there too, and you want to understand, where this decadal variability of this path variations come from. They are not unimportant, because for the Japanese fisheries and actually for the whole region there, you can imagine that this is these transitions are a big change in temperature. So in fish also collection. So well, basically this problem is also it's a very nice example of basically the problem, which is more abstract, and looking at probabilities of transitions in multi-stable stochastic systems. And this picture was saw it on one of the posters very quickly, where this tipping in climate has become very popular. Also, the funding of this 2-year project is also due to this popularity also. And people are interested in, in how can you go from one, say, sort of statistical steady state or statistical mean to another state, and when parameters are varied. And here you see the very, very simple, sketches in terms of 2 solenoids. We know that it's much more complicated, but these are sort of examples which are easily communicated. And particular interest is, of course, the noise-induced transitions, because here you still have, here you have to cross a bifurcation point. Here you have to cross a certain rate of a control parameter. This is the rate induced. But here, you're just in a multi-stable regime, and certainly you can have a transition. These are the most dangerous. So how do you approach that? Well, this is a problem which is posed, in other fields also, like in chemical kinetics, chemical reaction, physics, where you have a certain state, so that A, that will be the state here, at the top, for instance, and then you like to compute, say, transitions from state A to state B, and basically what you want to know is the probability that such a transition can occur within a certain period of time. So that's this tau here, and so it's the probability that you reach tau B, right, within a certain time tau, starting from XA. And this is a very general problem. And I think Tobias after me will talk about more on the theory also. So I won't do that. I'm interested from a computational point of view. So how do you compute this? And of course, you can do that, and people have done that, of course, in relatively, say, simple models, so small dimensional models like box models, or say reduced systems of ODEs. And the problem, we are interested in, okay, now you have an intermediate complexity model, and even, of course, you want to go further, like a sort of very high dimensional model. How do you compute these transition probabilities? Now, if the probability is high, then you could do a Monte Carlo, easily do that. But this in general, probabilities might be very low. And so then the problem is the probability is 10 to the minus 4, and you need to do 10,000 at least simulations, and that's usually not possible. Of course, in a simple model you can do that, but not with a model which has 1 million degrees of freedom. So this is the problem. Now, what have people done for that? And this is, of course, a big step. Use of rare event algorithms. So adaptive multi-level splitting and variants of that. And I guess also Tobias will talk about that. So I'll skip that. I'll just sketch you what happens. What we are particularly interested in one of the variants, which is called trajectory adaptive multi-level sampling. And there, what you basically do, and this is just a sketch, you start with an initial ensemble, which you want to keep as small as possible. And then what you do, you move that forward. And then based on values of score functions, which will be constructed to guide you to the transition, you will discard trajectories and you will branch off new ones. And the whole algorithm is constructed so that you do this sort of cloning and discarding of trajectories under this such that the statistic is the same, and such that you can actually compute, say, the transition probability using relatively small number of ensemble members and also a small integration time. And you can compute very small transition probabilities using this method. So here's some papers. It has been applied also in geophysical context, also to larger dimensional systems, particularly by Frédéric Boucher and by Eric Sommer and Roland, who was here, I think. Yeah, good. Yeah, good to see you, right? So there's there's actually very nice papers on, for instance, the transition in atmospheric jets. So that is already applied to, say, the barotropic vorticity equation, or with an application in Jupiter in the transition to jets. So what we want to do is basically build a more general approach. For the barotropic jet, there's a very specific, it has periodic boundary conditions, very specific fast solver where you can do a lot of trajectory computations very efficiently. In many of the models where, if you like to use, say, intermediate complexity climate models, that's not so easy to do. And so we're focusing on two things. One is the score function specification. This is very central. You can imagine if you have a lousy score function which will not guide you to the other state, that's basically difficult to reach. And so what we do in the project is basically look at this in collaboration with Frédéric Boucher to look at machine learning techniques where we base we actually from the knowledge of the previous trajectories computed, we make a machine, right? Can be a neural network, can be a reservoir computer, and basically try to optimize the score functions based on the previous data. I've chosen not to talk about that because it goes a bit more in the machine learning, and I'll focus on what's the other aspect, which is the dimension reduction. So you have a big system of PDEs, right? For of course, in the example we have only one equation, but eventually you want to apply that to say intermediate complexity climate models, and you need to be able to compute, say, the required trajectories. You need to compute basically trajectories in a reduced space. Otherwise, it gets too expensive. And we devised also a method for that, which is called projected time stepping method. Basically, what it does is it projects the equations in a reduced space, carries out the trajectory computation there, and then basically eventually computes in transform back. You can compute with times, you can compute, say, the transition probabilities. It's been applied here in this paper on a model of the Atlantic Meridional Overturning Circulation, which was also mentioned in one of the posters. And that is a model of dimension about 10,000 or so. So that is something, not too small, but already sizable. And what I want to talk about today is some new efforts, and I'm also interested, how people respond to that, whether that's useful or not. And that's basically the limitation of this bars et al. Method is that you fix the basis when you project. So it's like a low rank approximation for people who are a bit more numerical on that. So and how we fix the basis basically projected on EOFs. So those are the eigenfunctions of covariance matrix, which you can actually determine numerically by solving the Lyapunov equation. So that's a lot of technique, but it doesn't really matter. But the question is that you have to fix the basis. And so what we wanted is also a technique where you could apply to non-autonomous systems. So you try to make your basis variable in time. Now this is there's a nice technique which is called the dynamical orthogonal field approach. And what it does is basically it's sort of a stochastic Galerkin method. So what you do, you have your PDE here. So this is a stochastic PDE, which will eventually, the example will be our stochastic wind-driven ocean circulation model. And you have some noise here specified, which comes in the model from the wind. And what you do, you expand it into an ensemble mean and some patterns, which are called DO modes, dynamical orthogonal modes. And these Y are the coefficients of this mode. So it looks like a Galerkin approach, except that both the expansion, say velocities of vectors here, they are time dependent, and also the stochastic coefficients are time dependent, and also the ensemble mean is that. And now what you do is basically you have to get a closed system of equations. You basically use this dynamical orthogonality condition, which says that the change of the space in which you compute these probabilities are orthogonal to the original basis you have. And from there, and this is not this is work done by Temisapsis and Pierre Lamicheux. It's not big calculation actually to get a closed system of equations. And the nice thing, so this looks horrible, but I mean you see that this for the mean is just this is the expectation operator is E omega. So that just is the expectation of the right hand side. And then you do some projection here for the DO modes, where you have the covariance matrix of these coefficients involved. And then basically you have a stochastic equations for the coefficients. Now the nice thing is that you have a mean. This is a fully deterministic equation. These are also fully deterministic equations for the modes. So that means you have S plus 1 if you have S modes. Deterministic PDEs, and then you only have to solve a system of stochastic ODEs, so SDEs, for the coefficients, and that's cheap. So the expensive part is of course solving these PDEs for those modes. Now, if you do that, that works nicely. I had also a paper that Saps is not cited here, where we try to do that also for the wind-driven circulation. And you'll see that later also in terms of results, how that you can actually compute, say, the stochastic, so the interaction between the noise and the nonlinearities. Now,
But you still need to produce enough samples.
yeah, okay. Yeah, so what you do, I forgot to tell you that, I mean, you basically integrate this stochastic equation with a full ensemble. And you usually do 10,000 or so, because it's cheap.
Okay.
So in the later results we use 1,000, but in the work I did with Temisapsis, you use 10,000 or so, and that's very cheap. You can do that easily. So the disadvantage of this was that for every problem you have to set up these equations analytically. Then discretize the whole thing, and then solve those equations. That is really painful. Particularly, if the operator gets a little involved. So if you take a climate model with, switches or some strange nonlinearities in forcing functions or so, then it becomes awful. So first thing what we did was basically make a matrix version of that. So you can plug in only the right-hand side of your model and the Jacobian, if you have that. And basically, then the whole procedure basically works, and that makes it enormously wider applicable, because you can put it in the framework where you need to, as I said, only the right hand side and the Jacobian. Now this is just a formulation. You see, it's very similar. You have this x here, which is the vector of unknowns. You take this mean, right, and you take the modes, which are z, and then you expand this. This is the Calhoun-Lewis expansion in matrix form. You have some, say, dynamic orthogonality condition, which is here. And you can basically write it down here where this M operator here is usually in climate models, you have always, or even non-slopes, you have that, you have no time derivative for a continuity equation, for instance. So that's taken into account. And basically you have a relatively fast method to solve basically these equations in matrix form. But it's not efficiency here, it's just the applicability, which is easier. Now, how do you apply this now? Well, I thought, maybe you're interested in this hierarchy of models which are available for the Windswept circulation. So here, there's a few models also developed by Michael Gill, who's not here, but that started this modeling also in the reduced case, where you look at truncated models. So like Galerkin truncation, you truncate a number of modes, like the original Lawrence model was developed too. And there are different brands of those, and they actually give you, this first sort of behavior of the model if you say change parameters, in a limited way. Then you have a spatially projected model. So this is a model which is 1D, right? So this is a sort of a basin in the ocean where you only consider one direction. And then the models which are really this intermediate complexity models for the wind-driven circulation are, say, quasi-geostrophic or shallow water models. Now, quasi-geostrophic you usually only, say, use in really idealized geometry like square basins or rectangular basins. Shallow water models you can actually use, realistic ocean topography in there. And so typically here the degrees of freedom go from 1,000 to say 100,000. And then of course there's the larger models, which I sketched here very briefly, the kind of intermediate, but those are, the CMAP, the climate models. Of course, they're sort of ocean variants of that, etc. But what we're interested in just to pose here, the model where we're going to look at is this sort of model where you have a layer which is active, where you have flow, and then you have a layer below which is motionless, but it has a density a bit higher, and we put that in a rectangular box. And then you get the problem here. So this is just a bartotic, say, quasi-geostrophic model. You see that it looks a lot like the equation we already saw this morning, except you have this rotation effect, so this is planetary, say, rotation effect, and then you have the wind forcing. And the rest looks like 2D Navier-Stokes. So they basically recognize many of those details. And this is, of course, the sort of continuity equation translated in. And now this is just a relationship, not continuity, just a relationship between the vorticity and the stream function. And then you have a noise term, which basically we prescribe. So that's the noise in the wind. And we'll take a very sort of very simple configuration. So we have a, say, rectangular basin. We'll put a deterministic wind stress in there. And we have a noise pattern, with sort of a Gaussian in the basin. So it's relatively simple. And why do we do that? Well, because for this model and the deterministic case, the whole bifurcation structure is known. So this is a very old results, 20 years ago. It was actually earlier already that this was computed by many others, but also by us. So if you vary the Reynolds number, which is like 1 over the viscosity, right? So if Reynolds number increases and less viscous, then what you see, you have this, say, what we call a double gyre state, which becomes unstable. You get a pitchfork, then you get a limit point and another pitchfork, and eventually what you get some sequence of half bifurcations where the flow eventually gets chaotic due to an orbit. Now, for the transition probabilities, you'd like to focus on a simple example. So you take this regime here where you have, say, 2 states here, which are sort of a jet down state and a jet up state, and we forget about the rest. Now, if you look at, say, the first one step, I mean, to look at what happens here in terms of the pitchforks relationship, you can look at the eigenmodes. And what happens here, you have 2 eigenmodes of the system. They're real eigenmodes. And what they do is they reel on the symmetric branch, and then what they do if you get this pitchfork here and it gets asymmetric, then along this branch they deform and they eventually form an oscillatory mode here. This is a mode merger. This is in Reynolds, and this is the real part of the eigenvalue. You don't see the imaginary part. And that eventually gives rise to this Hopf bifurcation and eventually to Hopf orbit. So this structure is very well known, and it helps us to interpret the results on the transitions. So here comes this, when you do that with this dynamic orthogonal field method, so you solve the equations, and here is a standard case. So the Reynolds is 40, which is in this multi-stable regime. The noise is here 1, and this is the resolution of the domain, so 46 points, and we take 4 DO modes. And what you see is that black one is the mean. Then you see these modes eventually equilibrating. And if you look at the probability density distributions of the coefficients, which you get, am I through time? No,
more or less.
yeah. Oh, okay, good. Okay. Well, I'll go quickly through that. I have a few slides more. So what happens is that you get these probability distributions. You see that these modes are basically here. You see these modes, which are the eigenmodes of the system. You see that this is multi-stable, so you have a double peak. Now, I'll skip this one. If you look at transitions, so here is the, we have a total of say 5,000 say trajectories. Then what you're interested in is how many of those actually go to the other state. So this is going from one state to the other state. And then basically what we have is that you get 53, so you can compute the transition probability. Of course, you have to do that for so many cases, of course, to get statistics of that. But what is interesting, and that's what I want to focus on, is how does this transition path look like? And can we understand why the noise actually drives it into transition? And this is basically what you can see here. So here you have the slightly lower noise. And what happens is that this Y2 coefficient here basically increases in so here the Y2 coefficient, it increases in time, but it basically is not enough to actually cause the transition. And so what happens if you go to a slightly higher noise, then basically what happens is that the interaction of all those modes and the noise, they create a very high amplitude of this Y2 mode. And it gets from, say, very asymmetric, it gets very symmetric. And because it's so symmetric, it drives us to the other state. And this is the main result. Now you can understand that also based on energy transfer, where you look at the energy transfer, you see that indeed this is the energy transfer from all the modes to this, say, mode 2. And then you see that indeed there's a lot of energy transfer which occurs to this mode exactly in the transition phase. So then finally the transition path is that you can look at how this transition paths look like, and in the Y2, Y3 space with amplitude of Y1 here. And then you see that there's a very specific pathway where the noise interacts, give you the symmetric V2 mode. Then you get the transition, and then eventually all those say trajectories end up on the sort of the other state. Okay, so that was a bit in a nutshell, but so what we actually try to do now is to connect this dynamic orthogonal field method to TMS, because we now have a dynamical basis where we can actually maneuver in with TMS. It's not that trivial, but we have some first nice results. And then eventually try to build a more generic TMS code, also with this, say, reservoir computer approaches for commuter estimates. So these are the score function estimates, and then eventually want to try to apply that to three-dimensional ocean models. Thank you very much. I hope this good.
I'm curious, you mentioned like the DO approach applied to so right now it was a barotropic statistic equation.
Yeah.
So you said it was hard work to get the set of equations from the DO formalism.
Yeah, well, in the paper I did at 10 subsets, they just computed the equations.
by hand, but I'm
Yeah,
curious,
analytically.
you mentioned the 3D ocean model. So
Yeah.
that's a different class of models.
Yeah, that's right. But it's now set up in a way that you only need the right-hand side and a Jacobian of the system. And for many of those global ocean models, we have that.
Okay, so
that makes it that you can apply it.
Work for
Yeah, because if you want, I mean, if you could of course calculate analytically the equations, but it's yeah, you have to discretize again, and if you change something, it's difficult, and you have to do it, to add that. So it's just more flexible.
Okay, so you can do it in sort of non-intrusive way.
Exactly. Yeah. So yeah, code is in Python now also, so it's available on GitHub. So if people are interested, and we have support also. Yeah.
Okay.
I'm just curious, you mentioned that you have the computation for non-autonomous system.
Yeah.
There is any publication on that? Or could you provide just a bit more of detail of the concept behind that?
No, I mean, I don't think there's any publication on that yet. I think at least maybe the experts can maybe have a better overview of that, but I don't think so. I think TMS has just been applied so far to autonomous systems. Correct? Sure. Yeah. Okay. I have to
No, I got the impression that you say that it was a technique that can be applied also in that context. That's why I was curious about it.
Yeah, I think it can be applied. Yes, because if you have this DO, there's no limitation. You can put a time kind of forcing in there.
Yeah, but you need to compute them again and again.
Yeah, you have, that's right. So you have to freeze. At some point you have to freeze basis, and then look at this reduced space, and then see how the trajectories move over to the next time frame. Yeah, that's not easy.
Yes, thank you for the very nice talk. So let's say I have my DO reduced system, and I predict like the transition for certain noise path. Now I pick up this noise path, and I'm gonna drive the original system with those noise paths that led to transitions in the reduced state space. So would you see that at least statistically, not necessarily, you won't have like necessarily.
No, it's not one-to-one.
One-to-one, yes, I understand that. But statistically, like if you look at the probability of this distribution of these transitions, like do they agree to certain extent?
That's something to do. Yeah, it's feasible.
It's visible, but it's visible. Right?
Yeah.
We didn't look at that.
No, but I don't know. I don't think anybody looked at that also, even in the more conceptual models. Of course, there has been a lot applied to small dimensional models.
Okay, that's interesting.
Yeah, interesting. Yeah.
Because that's it's a natural question.
Yeah.
Some further questions? Okay. Thank you very much.